Okay, so in this lecture, first we talk about an example of the cyclic decomposition theorem. Rather, I should say an example of the rational form of a linear operator, and then we will be eventually discussing, or rather introducing, the concept of Jordan form of a linear operator. So let us start with the example first. Suppose you choose a linear operator on the space say R3, okay, such that I'm giving a matrix representation of this linear operator in terms of the standard ordered basis. Let's say for the standard ordered basis, which is given as, let's say, 5 minus 6 minus 6 minus 1 4 2 3 minus 6 4. Okay, 3 minus 6 minus 4. Now the uh, characteristic polynomial of A should be, so let f be the characteristic polynomial for A. Then it's quite relevant to see that f is of the form x minus 1 times x minus 2 whole squared. Okay, we know how the characteristic polynomial is find out, so it's of this form, right? We find the determinant. Let's take this x. Yeah, so this comes out of to be of this form. Okay, or rather, we often do it in the other way around. We do it as determinant of xi minus a to keep the sign of x to be supposedly positive. Okay, so if is of this form, and while studying diagonalization, we had previously encountered the fact that this is a diagonalizable matrix. In case of a diagonalizable matrix, recall that the minimal polynomial it splits into linear factors. So if the characteristic polynomial is of this form, the minimal polynomial p will have the same roots. So if it has the same roots and it splits into linear polynomials, so it should be of the form x minus 1 times x minus 2, right? Okay. So this is the minimal polynomial, and now we are concerned about trying to find a rational form of this matrix. Okay. First thing first, we know that if I consider a cyclic decomposition of this of the vector space R3 under this linear operator, then the first non-zero vector we get, the t annihilator of this vector will eventually come out to be the minimal polynomial. So if alpha 1 is the first non-zero vector uh, related to the, I'm writing it in short form, okay, to the cyclic decomposition theorem, then P1, P1 which was the T annihilator of alpha 1 should be equal to P, right? And so if P1 is equals to P, then it's obvious that the dimension of the T cyclic subspace generated by alpha 1 T should be of the degree of P1, right? So the degree of P1 is 2, so it should be of order 2. I mean the dimension should be 2. But the dimension of the given vector space is 3, right? So that means there exists some other non-zero vector as well. So therefore there exists some other non-zero vector alpha 2 such that the dimension of the T cyclic subspace generated by alpha 2 should be 1, right? Is this part clear? Okay. Further, if we recall the fact that if the dimension of the T cyclic subspace generated by some vector alpha 2 is equals to 1, then that eventually implies that alpha 2 is an eigenvector, right? Is an eigenvector for T. Clear? Rather, we are not concerned about that as much. We are more concerned about the fact that from the generalized Cayley-Hamilton's theorem, recall that P1 considers this form, alpha 2 will also have a T annihilator, let's say P2, then F should be of the form PP2, right? P times P2 or P1 times P2. whatever you may think it of as. So what should be the choice of P2? So the choice of P2 is exactly x minus 2, right? Right. So alpha 2 can be thought of as an eigenvector corresponding to the eigenvalue 2, right? Okay. So we have got the T annihilator of P2 as x minus 2. We have got the T annihilator of alpha 2 as x minus 2. The T annihilator of alpha 1 is x minus 1 times x minus 2. So we have got both the T annihilators. Right, we have got both the T annihilators. Now, what should be the rational form of this matrix? Now, recall how did we find the rational form? What we used to do is that, so T is given a linear operator on R3. We have two T cyclic subspaces, right? This and this. Okay. What we used to do is that we used to restrict T to these subspaces, right? We to restrict T to these subspaces, and the minimal polynomial of this should be then x minus 2 by definition, and this should be then x minus 1 times x minus 2 by definition. Just go through the previous lecture, you will be able to understand these facts. This is also kind of coming from the primary decomposition theorem, which we relate as well. So yeah, um, so T1 has a cyclic vector, right? T1 has a cyclic vector alpha 1, T2 has a cyclic vector alpha 2. So T1 has a representation of the companion matrix of its minimal polynomial. The minimal polynomial is this. We can expand this to write it as x square. Then we have minus 3x plus 2. So the companion matrix representation should be of the form. So we just write it here. So we have 2. Yeah, we had minus p0. So minus 2 and 3 here. And then we have 0, 1. Right? This is the companion matrix representation. And in this case, it should be just 2. Right? So therefore, we know that the T can be written as a direct sum of these linear operators T1 and T2. Eventually speaking, A can be written. Suppose this is A1 and suppose this is A2. Then A is a direct sum of these matrices, which we write it as A1, A2. Right? So if you just place it right there, you get 0, minus 2, 1, 3. Then we have 0 here. You have 0 here as well, because this whole part is 0, right? This is a 2 cross 2 matrix, so it will obviously relate to the dimension of A1. This will relate to the dimension of A2 as well. Here you have a 0, sorry. Okay, here you have a 0, 0, and you just place A2 here, so you have 2, right? So this should be the rational form of A. Clear? Clear? If I quickly recall the concept of a companion matrix, then let me just recall this. Companion matrix for a polynomial P. Suppose the polynomial is given in this form. Suppose it's x to the power n plus cn minus 1, x to the power n minus 1, monic polynomial. And so on and so forth till c1x plus c0. Then the minimal polynomial comes as, so it's an n cross n polynomial. You have the last column given as minus c0, minus c1, all the way up to minus cn minus 1, and the other part it comprises elements of this form. So 0, 1, all rest of the elements are 0. You have 0, 0, 1, the other elements are 0, and it continues. So eventually you will get this element as 1 and all the elements are 0, and the pattern continues. Right? So this is the companion matrix. Okay. Yeah. So we have got a example of the rational form of a matrix. Now let us dive into introducing the concept of the Jordan form of a matrix. We will supposedly consider two lectures on Jordan form, and then we will be moving on to computing invariant factors of a given linear operator in terms of its matrices, because that's more useful a topic. Okay. So wait a sec. Let's just go to the last page once. Okay, one sec, guys. Yeah. Okay. Yeah. Let's start from here. Let me just write it as the Jordan form. The Jordan form. Okay. To understand the Jordan form, the first thing we need to understand is the concept of the analog of the cyclic decomposition theorem for a nilpotent operator. Okay. So what is a nilpotent operator? If you recall, definition, let V be a vector space. Let V be a vector space. A linear operator. A linear operator N on V is said to be nilpotent. Is said to be nilpotent if there exists a positive integer r such that n to the power r is the zero operator and r is the least positive integer to happen so, and n to the power r minus 1 is not the zero operator. Okay, so this is the precise definition of a linear operator. Now suppose we have a finite dimensional vector space V. Okay, so let V be a finite dimensional vector space and n is a linear operator defined on V. Okay, therefore by the cyclic decomposition theorem, by the cyclic decomposition theorem, we have r non-zero vectors, or I should write it as we have some positive integer r, then you have vectors alpha 1, alpha 2 till alpha r in V. Okay, and respective t annihilators which you write as p1, p2 till pr, such that V can be decomposed into the cyclic subspaces generated by each of these vectors, right? So you have alpha 1, so respective n annihilators I should say, because I am talking about a nilpotent operator n. So n, then you have alpha 2, n, and so on till you have the last one, right? Yeah, correct. Okay, and such that pi plus 1 divides pi. Is it clear? Now from definition we know, or rather should I say from the proof of the cyclic decomposition theorem, we know that the t annihilator of alpha 1 is the minimal polynomial for it, right? So now we can write say that now p1 is the minimal polynomial for n, right? From the previous lecture, recall the characteristic polynomial of n if n the finite dimensional vector space is having dimension n, then the characteristic polynomial is of the form x to the power n, right? So p1, therefore p1 should be of the form some x to the power k, let's say, such that k is less than equal to n. Okay, so V be a finite dimensional vector space of dimension n, let's say. Is it clear? Okay. Okay. Now, since each pi plus 1 divides pi, therefore we can say, therefore for all pi we have the representation for pi as it's of the form x to the power some ki, right? Right. Further, further, because each, so P1 is of this form, right? And Pi should be of this form, right? So x to the power ki, because as each Pi will divide P1 for sure. On a general note, Pi plus 1 divides Pi, right? So further what we have is that, so if every Pi plus 1 divides Pi, then the powers should should decrease as the index I increases, right? So further, then K1 should be greater than equal to K2, this should be greater than equal to K3, and so on and so forth till Kr, right? And it's obvious that where K1 should be equal to K, right? Okay, and this Kr should obviously be greater than equal to 1. Clear? Okay. Now, what is the companion matrix for Pi? The companion matrix for Pi, which is equals to x to the power ki, is surely of this form, right? So you have 0 1 0, then you have 0 0 1 0, and so on till running. You have 1 here, all these elements are 0, and the last column are all 0 elements, right? Because you have no coefficient here, right? So it's 0 times ki minus 1 and so on, right? So the companion matrix is of this form, and so if you consider, so this matrix is called the elementary nilpotent matrix. This matrix is called the elementary nilpotent matrix. Now, from the observations in previous lecture, it's for sure that then n, that there exists an ordered basis for V such that n is a the matrix of the nil. So the matrix of n is a direct sum of all these individual matrices, right? So we can think of it as saying it as in this form that, so therefore there exists an ordered basis, therefore there exists an order. Okay, one more thing is that this matrix will have dimension ki cross ki, so therefore there exists an ordered basis B of V such that the matrix of n with respect to B is a direct sum of the matrices A1 A2 so on till AR, where AI is the Ki cross Ki companion matrix, is the Ki cross Ki companion matrix of the polynomial x to the power Ki, right? Which is also denoted as Pi. Furthermore, we know that K1 is greater than equal to, since K1 is greater than equal to K2 and so on till Kr, therefore the blocks, the block matrices decrease in size, the block matrices decrease in size as one moves from left to right, moves from left to right. Clear? Okay. Now we are concerned about what this integer r is specifically. Okay. So now let me claim the fact. Claim that R is basically the nullity of the nilpotent matrix N and nilpotent operator N. Okay. So proof. So how do we prove this? We choose an element from the null space. Let alpha be an element from the null space of N. Okay. Then obviously by the cyclic decomposition we can write alpha as some f1t alpha 1 and so on till some frt alpha r, right? Sorry, we are using a nilpotent operator. It should not be t, it should be n. Writing t is a force of habit. Very sorry. Yeah. So we have this form, right? But alpha is the null space, right? But that implies the null space, or sorry, the n of alpha is 0, right? N is the operator. Let me use the uh, form the null space of it. Okay, so n of alpha is 0, right? So if n of alpha is 0, then what we can say? Then we can say that the n of each fi n alpha I should be 0, right? By the independence, we can say, right? But that implies now, obviously, if you have a linear operator of this form, let's say you have a0 plus a1t and so on till an t to the power n, let's say, then what is t of this? So it's simply a0t plus a1t squared and so on till ant to the power n, right? So if this is of this form, let's say it's of the form gt, then g of x is of this form, right? So it's a0 plus a1x and so on till anx to the power n, and t of this, that is t of gt, is nothing but this, which is exactly equal to x times gx of t, right? Clear? So we will use that very fact here only. Okay, let me just rub out this part. Okay, yeah, let's continue. Okay, furthermore, I should be using this fact where FIs are polynomials with degree of FI less than KI. Okay, degree of FI is less than KI. So this happens. So that implies we have x times Fi, this under the linear operator n, the nilpotent operator n of the vector alpha. This should be equal to 0, right? So if this happens, so this clearly means that x to the power ki should divide xfi, because x to the power ki was the n annihilator of alpha I, the n annihilator of alpha I, but the degree of fi was considered to be less than ki, so that would imply that fi is of this form some ci times x to the power ki minus 1, where ci's are scalars, where each of these ci's are scalars. Clear? Okay. So therefore alpha has this form, right? So it's of the form c1 times x to the power k1 minus 1 n of alpha 1 and so on till cr x to the power kr minus 1 of n times of alpha r. But this specifically means that the null space is spanned by, that the null space uh, has the basis elements which are n to the power some ki minus 1 alpha, right? Because alpha is spanned by these vectors, right? And there are r of them. So we get two observations, that is null space of the nilpotent operator n is having the basis elements of this form, and moreover, since there are r number of elements, so the dimension of the null space should be r, or that is the nullity of the nilpotent operator should be r. So this also implies that the nullity of n is r, right? So I guess this is clear. Okay. So now what we try to do is that now we want to introduce an arbitrary linear operator with a given characteristic polynomial and to see how can we get a Jordan form, what we call a Jordan form of that very linear operator. Okay, let's go to the next page. Okay. Now we choose a linear operator on a finite dimensional vector space. One sec. Yeah, okay, so let T be a linear operator on a finite dimensional vector space V over F, let's say. Okay, and the characteristic polynomial of T is given as f is equals to x minus c1 to the power t1, x minus c2 to the power t2, so until x minus ck to the power tk, let's say. Okay, where c1, c2 till ck are distinct elements are distinct elements from f, right? And these di's are greater than or equal to 1. Then obviously the minimal polynomial will divide the characteristic polynomial, and the minimal polynomial will comprise of the same roots of the as the characteristic polynomial. Therefore, the minimal polynomial p should be of the form x minus c1 to the power r1, x minus c2 to the power r2, and so on till x minus ck to the power r, right? Where obviously ri, each ri is less than or equal to di greater than or equal to 1. This happens for all I. Now we try to apply the primary decomposition theorem here. So if Wi is considered to be the null space of, let me write in full form, the null space of this part, that is t minus ci all to the power ri, then by the primary decomposition theorem, recall by the primary decomposition theorem, we have so we will have a direct sum decomposition of V, right? So we will have V as W1, direct sum W2, and so on till Wk, right? And the minimal polynomial for each Wi will be this polynomial x minus c2 to the power ri, x minus ci to the power ri, and the minimal polynomial for Wi, sorry, the minimal polynomial for Ti, which is T restricted to Wi, is x minus ci to the power r, right? This is straight away statement of the cyclic decomposition theorem. We are intended to define a nilpotent operator on the subspace Wi. Okay. So define n on, so define a linear operator n on Wi such that this n is equal to Ti minus Ci. Okay, clear? Now n is clearly nilpotent, right? So therefore n to the power ni, rather I should say ni here, ni. So ni to the power ri will be 0, right? Because Ti minus Cii whole to the power ri will be 0. That is the minimal polynomial exactly of the subspace Wi, and Ti is nothing but T restricted to Wi. So it's clear, right? So which implies ni is and also due to the fact it's the linear polynomial is of this form, so and ni to the power ri minus 1 is not equal to 0, so clear for ni is a nilpotent operator for sure. is a nilpotent operator. Clear? What should be the minimal polynomial for Ni then? It should be x to the power ri, right? With minimal polynomial x to the power ri, right? Now, how can we define Ti on Wi? Therefore, on Wi, the linear operator T can be expressed as, right? Because Ti is an expression for T restricted to Wi. So we can talk about T being expressed on Wi. So on Wi, T can be expressed as Ni plus Cii. So that is I am talking about Ti can be written as Ni plus Cii, right? Right. Now what is the matrix representation of Ni? So the matrix representation of Ni is of this form, right? So Ni has this form. So it's of the form 0, 1, 0, 0, uh, 0, let me just prodify it. So I'm trying to just frame out a matrix representation of this, right? So now the matrix representation of T then will have form under some ordered basis. I'm not concerned about the basis at all because we have already observed the fact that there exists some basis under the linear operator, sorry, under the vector space given, so that Ni has a form which we had observed previously. That is, so it precisely of this form, right? Ci times I, but Ni will have this form, right? So it will be of the form 0, 1, 0, all the elements are 0, 0, 0, 1, all the elements are 0, and the last column is completely 0, and here you have another 1, 0, and 0, right? This is the form. Then you have plus Ci times the identity operator, right? Identity matrix, right? So what should this give you? So this should be giving you this form, right? So C, 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 and all the diagonal elements are C. Below you have 1, 1, 1. Here you have another 1. Should see here you have another 1, and all the elements are 0, right? Right? Where, so I am considering each C to be Ci, where C is Ci. Okay, clear? Furthermore, we know that in this in the case of an Ni, the matrix of Ni, if you consider the matrix of the whole linear operator T, then it comes out to be a block form of each of the matrices in I, which decrease in size as one moves from left to right, right? Therefore, the matrix T, if I consider the whole matrix T, then it's some direct sum of these matrices in block form, right? So if I consider this to be the matrix, say Ji, then you will get some form. I will discuss that obviously, but let us first discuss about this very matrix set only. So furthermore, the sizes of these matrices will decrease as one reads from left to right. It will decrease as one reads left to right. Okay. A matrix of this form is called a Jordan canonical form, elementary Jordan canonical form. It's called an elementary Jordan matrix with characteristic value C. With characteristic value C. Now, I guess the rest of the portions are clear from the previous observation that if you consider an ordered basis B of V and you consider the matrix of the whole linear operator T in terms of V, so suppose this is A, then that should have a block diagonal form of this form, right? So A1, A2 till A K, where each of these AIs are each of the elementary Jordan matrices, right? So it's of this form. It should be of this form. Let's say J1I, J2I, and so on till JNI, right? So it's Ni cross Ni, right? This N cross N. Clear? Where each JJI is an elementary Jordan matrix of characteristic value Ci, right? Right. So an n cross n matrix will satisfy this condition, or also I should add this as also within AI, also within AI. The sizes of the matrices, the sizes of Ji decrease as J increases, right? Decrease as J increase, small J increase. An n cross n matrix will satisfy this condition. That is a matrix of this form, or I should say of this form. Rather, I should say of this form. Combinedly, okay. Combinedly, it's called an it's called an Jordan form. This is called a Jordan form matrix. Okay. So the algebraic introduction to the Jordan form is, I guess, done. So from the next lecture onwards, we will be concerned about computing the concepts of Jordan form under matrices. Okay. So we do guys in the next lecture.